In this video, we're going to focus on rotational energy and some of the situations in which it can be helpful or at least apply. And when we're defining rotational energy, we're specifically talking about kinetic energy, which in this case has to do with a collection of mass that's all rotating about a singular fixed point. And so a good example of that you can imagine down here is something like a rigid pendulum like we've got, that's rotating about this point where the pendulum is attached to. If we imagine all of the mass in this pendulum all rotating about that point, then you can imagine that every single little bit of that total mass is all rotating at different radii, at different speeds, linearly, but they are all rotating still with the same angular velocity. And so in a previous video, we showed how we can quickly derive a form of rotational kinetic energy, and we're going to be working with that here in a more pure energy sense, where we're going to be combining it with other forms. So to start out, I'm going to write out that initial equation that we're going to use again, and that's that the rotational kinetic energy is equal to 1/2 times the rotational inertia of the object in question times the angular velocity squared. Now, if you note, this is very similar to the translational kinetic energy formula, where 1/2 is still definitely 1/2. The inertia of an object, its mass, is the rotational inertia, and the translational velocity of the object turns into the angular velocity of the object. So again, rotation has a lot of these one-to-one relationships when going from one equation to the other. The last thing that we need before we get started and playing with this a little bit is that when you are finding the gravitational potential energy of an object, particularly one that could have a lot of pieces at play, like this pendulum down here, generally, it's worth remembering that the height should be measured to the center of mass of the object. And with that, we're going to start playing around with this rigid pendulum down here. This first example with the rigid pendulum involves a heavy block with a mass of 3 kilograms that's attached to a rod, also of mass m, so also 3 kilograms, with a length of 2 meters total. Now, this rigid pendulum is displaced 37 degrees from the vertical and it's released from rest. And yes, we can treat the block here as a point mass, so we don't need to worry about its distances or lengths. Now, to start out, eventually we're going to be applying conservation of energy to this to figure out the speed of the block as it passes through equilibrium. But in setting up some of that, one handy thing to do right off the bat is figure out exactly how high up this thing's center of mass was raised so that we know how much it is set to lose and gain in the form of kinetic energy. In order to do that, we need to start by finding the center of mass of the pendulum. So let's do that first, and then we'll figure out how high it gets raised after the fact. Now remember that the center of mass of an object generally is all of the masses multiplied by all of their respective distances away from some reference point, which let's just go ahead and make this attachment point up here. And then you divide that by the total of all of the masses combined. So in setting that up, well, we have really two masses that we need to consider and combine together. We've got the center of this rod here, and we've got the center of the block. Now, the center of the rod is at a distance L/2 away from the attachment point. So over here, our first combination of mass and distance is going to be mass times L/2. That's the rod. And then added to that is going to be this block here at the end. That's going to be mass times the distance of L away. And then divided by that is the total of all of the masses that this object is made of, which is just going to be m plus m. Simplifying that a little bit, we could turn the top half here into 3/2 L, or ml, and then the bottom half here is going to turn into 2m. That means that the center of mass, well, we can cancel out that m there, is going to be 3/4 L, or 3/4 of the way down the length of the rod. Which, if you think about it, makes sense, because that's about the halfway point between the two masses that we picked out earlier. Now, the next thing we need to do is figure out how high that center of mass was raised from its original position when the rod was just at equilibrium over here. In order to do that, we can use a trick that is applied a lot of the time in a ballistic pendulum type problem, where we know how far away from the pivot point the center of mass is by taking this distance right here, which remember is 3/4 L, and finding this distance right here, which would be 3/4 L times the cosine of this angle right here. Now, at that point, if we take the original position of the center of mass, which let's just say is right here, then this distance right here all the way down is also 3/4 L. And so if we find the difference between those two distances, the 3/4 L and the 3/4 L cosine theta, what we're left with is this distance right here, which if you notice is the exact amount of distance that the center of mass gained from start to finish. So in order to figure out the height h, I'm going to call that capital H. It's going to be 3/4 L minus 3/4 L times cosine theta. And at this point, it's probably for the best if we start simplifying or plugging in some numbers. So we can simplify this down to 3/4 L times 1 minus cosine theta. And at this point, if we plug in all of our numbers, the length of the rod and the angle theta, we will find that the center of mass of the pendulum was raised by a whole 0.3 meters. Doesn't sound like a lot, but it's going to still turn into some speed that we can work with. So that's where we're moving on next. The next thing we need to do is figure out the moment of inertia of the pendulum. This is important because we're going to be plugging it into our rotational kinetic energy formula later. So this pendulum is made up of a large rod rotating about one of its ends and a point mass, essentially at a distance L away from the pivot point. If we put all that together, that means that our rotational inertia is comprised of the rotational inertia of that rod plus the rotational inertia of the point mass, which we'll just say is a point mass. The formulas for each of those are 1/3 ml squared for the rod and just regular ml squared for the point mass at a distance L away. Combining those together, we would get 4/3 ml squared, and plugging in our numbers, we would end up with a rotational inertia of 16 kilogram meters squared. And once we have that, we're ready to proceed to the energy phase. The final step here is to use conservation of energy to figure out the speed of the block as it passes through equilibrium. We're going to have to first find the rotational speed, and then we can use that to figure out the linear speed fairly easily. So conservation of energy just means that we need to figure out the total amount of mechanical energy up front, and we know that that should be equal to the total amount of energy at the end. Now, the total amount of energy at the start really is just gravitational potential energy. At the end, we're going to assume that we only have rotational kinetic energy here. So setting that up, our gravitational potential energy is going to be comprised of two masses. So 2m times the acceleration due to gravity times that height h that we solved for earlier. That's 0.3. And that's going to equal 1/2 times the rotational inertia, which we've already solved for, times the angular velocity omega that we're trying to solve for. Rearranging that, omega would then equal the square root of 2 times, well, we could really make that 4 times m times g times that height we solved for divided by the rotational inertia of our system. Plugging things in then, we would get a angular velocity of about 1.5 radians per second. If we wanted to turn that into a linear velocity, which is usually more useful, we could simply use the relationship that the linear velocity equals the radius times the angular velocity. So knowing that the length or the radius here is about 2 meters and the angular velocity is 1.5 radians per second, we can very quickly find that the linear velocity is going to be about 3 meters per second. And that is our answer. So this rod, once released from rest, will pass through the lowest point it reaches at approximately 3 meters per second. Cool. Now we're going to move on to another familiar setup. Our next example here has to do with the Atwood machine yet again. This time we're going to be applying energy to it. It's the same setup as the last video where we've got a solid disc pulley with a mass m and radius r, and it's got two masses, m1 and m2, suspended on a cord from either side of the pulley. These masses are released from rest. M2 is the heavier one, and M2 accelerates downward through a distance of d. I'm going to draw that distance that it's falling down here. And for the sake of helping us visualize things, I'm going to say that M1 starts on the floor when this starts to fall down. Although even if it didn't, the logic that we're about to apply would work all the same. Now, the first part here we need to do is figure out the total mechanical energy before and after. There aren't really any complex objects to find the rotational inertia of, and this problem in particular, I do find to be a little bit easier if we don't worry about the center of mass of the system. Now, before everything happens, before everything starts moving, this mass 2 block is really the only thing storing energy in the system. Mass 2, if it were not higher than mass 1, this system wouldn't really go anywhere. mass 2 is the block that wants to travel downwards. So in talking about the initial mechanical energy, really all we have is potential energy from that mass and the distance that it stands to gain. In that way, the initial mechanical energy is really just going to be the potential energy from mass 2, which would just be mass 2 times g times the distance it's about to fall through, which is that distance. That's the initial mechanical energy. For the final energy, we have a lot of things at play in this system. So let's think about it. Once mass 2 is just about to hit the ground, we have mass 1 that has been lifted up by an equal amount. So whatever mass 2 lost in distance by traveling downward, mass 1 is going to gain. So mass 1 being lifted up means that it technically now does have potential energy, even though the system's going to continue in that downward direction. Having to lift mass 1 up takes away kinetic energy from the system that it would have otherwise gained without it there. So for the final energy, let's start keeping track of some stuff. So yeah, we are going to have some potential energy stored up in mass 1, for sure. In addition to that, we are going to look at the case in which these masses are just about to stop moving, like M2 is just about to hit the ground. In that case, remember that these masses are connected by a cable. Their fates are intertwined. One is not going anywhere without the other. Because of that, both masses are going to be moving simultaneously. Furthermore, because they're connected by a cable, both masses are confirmed to be moving with the same velocity. So we're going to have this interesting situation in which we have kinetic energy of mass 1 added to the kinetic energy of mass 2. And these are both translational kinetic energies, not rotational. These masses are not rotating. Finally, we have the star of the show, which is this pulley over here that does have mass. Now, this pulley is going to be moving along with the masses, and so it's going to have the same kinetic energy, but this time it'll be rotational. So let's just call that KER. So writing this whole mess out, we're going to have M1 times the acceleration due to gravity times the distance that it gained. So now it's d meters high up, plus I'm going to combine the kinetic energies of the two masses that are translating. So that'll be M1 plus M2 times the same velocity, v squared, plus 1/2 times the rotational inertia of the disk pulley over here, times the angular velocity of the pulley. And this big, gigantic mess right here, with all three terms, is the final total energy of the system after mass 2 has fallen downwards. For the final step, where we find the expression for the velocity of the masses after they've fallen that distance, I'm going to highlight these equations just so it's a little easier to keep track of them. And what we want to do now is simply start out with a statement of conservation of mechanical energy, which is just that this initial energy here is going to equal the final. And if we go ahead and substitute, it's going to be m2g times d, and all of that is going to equal m1 times g times d plus 1/2 m1 plus m2v squared plus 1/2 times, I'm going to go ahead and substitute in the rotational inertia of the disk, which, if you recall, is going to be 1/2 times its mass, m, times the radius of the pulley, r squared. Then the angular velocity can also be put in terms of the velocity we're actually trying to solve for, which is the translational one. Angular velocity is v over r when you're replacing angular velocity with it, and remember that that is squared. Now, there's a couple of things we can cancel out here. First off, this is an r squared divided by a r squared over here, so we can get rid of those. We can turn that 1/2 times 1/2 into a 1/4, but let's go ahead and start rearranging some things to get more of the velocities on the same side. So on the left side over here, let's go ahead and put our m2 and m1 times gd over on the left side. And because they both are multiplied by the same factor gd, we can pull the m1 and the m2 out. Then on the right side, let's simplify some of the stuff over here. We would have 1/2 times, in a big group of parentheses here, m1 plus m2 plus 1/2 m over here, pulling out a 1/2 from both of these terms. And then all of that is multiplied by v squared, because both of these terms over here still have a v squared attached to them as well. That simplifies this equation by a lot. And so if we want to solve for v, the last thing we got to do is really just move this whole term over to the other side and then square root. So let's go ahead and do that. V squared, flipping things around, is going to equal 2 times m2 minus m1 GD, that's this left side, divided by our big collection of masses over here, m1 plus m2 plus 1/2 m. And the last thing we need to do is, this is still a v squared, so if we square root both sides, then our final equation for this Atwood machine will be this big chunky mess right here. These are two fairly complicated examples where you could see yourself applying rotational kinetic energy in the future. Now in the next video, we're going to be showing how we combine those two together, those two types of kinetic energies, into a rolling object. So stay tuned, don't forget to subscribe, and I will catch you on the next one. Peace.